Good night to everyone. In this episode of the podcast, we will introduce key concepts related to two fundamental radio frequency and microwave building blocks, oscillators and mixers. Specifically, we will discuss oscillator based on a non-dielectric resonator optimized for low phase noise and a double balance mixer, widely used in frequency conversion stages. We will outline their operating principles and review the essential elements of their design. So, let's get right into it. For the first part, the goal is to design a low phase noise RF oscillator, which converts DC power into a periodic AC signal without explicitly requiring an AC signal at its input. We will obtain this circuit by using a high Q non-dielectric resonator and an active device that provides effective negative resistance.
The basic structure consists of a resonator circuit connected to an active circuit. The resonator sets the oscillation frequency, while the active device compensates the resonator losses and determines the output level. The loop operates at a resonant frequency omega0 of the resonator, which is either 1 divided by the square root of Lc or the eigenfrequency of the cavity. This must satisfy the Barkhausen conditions at omega0, where the loop gain is equal to 1 and the total phase shift is 2 pi times the frequency. During the startup, the loop gain must be greater than 1, and in steady state, the nonlinearities of the active device drive the loop gain back to unity. To achieve low phase noise, we maximize the resonator Q and use a low noise active device. In our design, this will be accomplished using a air-filled coaxial cavity resonator, which will be described in the next slide.
We choose an air-filled coaxial cavity resonator as the frequency-selective element. It is essentially a section of a coaxial line with an inner and an outer conductor used at resonance. The line is usually short-circuited at one or both ends to create a standing wave, and its typical lengths are a quarter of a wavelength or half a wavelength at the desired frequency. To achieve a high Q factor, the resonator should be air-filled or use a very low-loss dielectric and be made of high conductivity metal. The dimensions of the coaxial line, specifically the ρD of the inner and outer conductors, are chosen to support the transverse electromagnetic mode and minimize conductor losses. Finally, the resonator is placed in a shielded and mechanically stable structure, which reduces radiation losses and helps prevent frequency drift. This type of resonator provides a very high unloaded Q, which directly helps reduce phase noise. The active device, such as transistor, is biased so that at resonance frequency, it presents an effective negative resistance that compensates for the losses of the resonator. The cavity is weakly coupled to the transistor or to the output through a proof or a loop. This coupling level determines the loaded Q and the output power. Here we have a clear trade-off. A stronger coupling gives us more power, but it also lowers the loaded Q, which results in worse phase noise.
For the last part of this topic, we will be discussing how a balanced mixer works. This device uses 4 diodes arranged in a ring that are controlled by the local oscillator signal, which alternately turns on the diodes on the left and on the right side of the ring, so the circuit keeps switching between two conduction states every half cycle. Because of the symmetry of the diode ring and the transformers, points A and C of the figure behaves as virtual grounds for the RF signal, which then splits into an in-phase and a counterfeit version of itself. As the local oscillator keeps switching the diode pairs, the mixer alternately sends the in-phase and the out-of-phase RF component to the IF port. The switching action is equivalent to multiplying the RF by the LO, and the result in the IF output contains the sum and the different frequencies. This kind of mixer is called double balance actually because both the RF and the LO signals are cancelled at ports where they should not appear, giving the circuit very good isolation and strong rejections of noise and spurious LO components.
Thank you for joining us today and see you in the next episode.